Good morning. This is, I guess you could say, part two of your notes for formal trig. And I haven't decided yet when I'm going to have you guys watch this. I'll either give you guys some practice on Tuesday and have you watch this Wednesday, or I might have you watch this tomorrow, so Tuesday, and then practice on Wednesday. But either way, this is I guess you could say the cream of the crop here. This is really the main event of this new unit, the newest material that you will see. We've done a lot of prep work, so leading up to it, just a review. We've got our trig functions sine, cosine, and tangent. And the ratios, so the sine of theta equals opposite over hypotenuse, the cosine of theta equals adjacent over hypotenuse, and the tangent of theta equals opposite over adjacent. The way we remember that is through the acronym SOHCAHTOA. When you are given a triangle ABC, you label the opposite sides lowercase a, lowercase b, lowercase c. And here's a table as a guide for how you would do the opposite adjacent hypotenuse labeling. We've set it up so that we can use that trigonometry in order to solve problems where we are given side length and we're given an angle and we're trying to find the missing side length that they're asking for. So in part 4, so you're going to want to get your note sheet out from the previous day that we took notes, or take out the note sheet, or take out the note sheet where you were writing your own notes if you didn't have the ability to print. And what I would like you to do is pick up where we left off, and so that is on this part 4, solving for missing side lengths. Our goal is to figure out what the side length of x is. And now, you'll notice with the sine, cosine, and tangent, there's really 3 items that we're looking at here. We're looking at theta, we're looking at one of the side lengths, and then we're looking at another. So there's 3 pieces here. If we know all 3 of them, then it should give us an equivalent equation in the end. I'll show you guys that once we solve one. And then when we are given 2 pieces, one of them is unknown, and we need to solve for that unknown. And so in this case, that's what we're doing. So they give us the angle, and that's our theta, that goes along with our trig function. And then they give us the 7, which happens to be across from the right angle here. And so the 7 is our hypotenuse. Now, our unknown is x. Step 1, what is the relationship between the angle and x? Is x the opposite side, or is x the adjacent side, or is x the hypotenuse side? Quick tip, it will never be the hypotenuse, because the hypotenuse is always across from the right angle, and we will never ever use the right angle in this trig to solve. So we've got 2 options, either the opposite or the adjacent. Well, 35 degrees in the x, side length x, is across from 35 degrees. So that means it's the opposite. So we've got an angle, we've got the opposite side, and we've got the hypotenuse. Opposite, hypotenuse. Opposite, hypotenuse. Opposite, hypotenuse. We need to use sine. So this is where that acronym comes into play. You identify what pieces you have, and then you need to use the correct trig function that goes along with those pieces. So we're using sine. And the way we set it up is exactly how we see it in this previous page. The sine of theta equals the opposite side length divided by the hypotenuse. So I'm going to set it up that same way. The sine of 35, we actually know the angle. The sine of 35 degrees equals the opposite, which is x, divided by the hypotenuse, which is 7. This is similar to that worksheet I gave you guys last week where you were solving for fractions and ratios, where at this point we know the sine of 35, and I'll show you this in a second, That's a number. That's a decimal. X is an unknown variable. 7 is a number. We always want to solve for the unknown, whether it be x or whether it's theta, the missing angle. In this case, we know the angle, but we don't know x, so we're going to solve for x. How do I get x by itself on the right side, right? If I hone in on where's my variable x, how do I get it by itself? Well, if it's x divided by 7, how do I undo division? I multiply by whatever it's being divided by. That cancels it out. So if I'm dividing by 7, I should multiply by 7 in order to cancel out that 7. So if I do it to the right side of my equation, I need to do it to the left side. So x divided by 7 times 7, I drew my line through it. It crosses out. But I have 7 times the sine of 35 degrees on the left side. What is that? How do we figure out what that number is? And that's where I'll show you. So again, we cancel it out on this side, and we're left with x equals 7 times the sine of 35. Now, I draw this in a linear, right, vertical, step-by-step way because I want you to see what pieces are equal. The x goes down here, it's by itself. 7 travels down, being multiplied by the sine of 35. How did I get from the sine of 35 to this decimal? And that's where I want to go to my calculator. You're going to want to make sure you do a couple of things. First, on your calculator, you want to make sure that this is in degree mode, right? Because we're talking about degrees here, 35 degrees. So hit this mode button, and we're going to have a bunch of options. It's a little bit overwhelming, but what we really care about is this row right here where it says radian and degree. You want to make sure that you're highlighting degree. Radian is something that you'll learn in Core 3. So radian degree, we want to be on degree, and I am. I'll exit that window. Now notice we've got our trig functions, sine, cosine, tangent on our calculator. There's nothing fancy that we need to do other than the sine. So what am I doing? The sine of 35 degrees. Sine of 35 degrees. And that equals 0.573576436. I rounded it to about 3 decimal places, or I cut it off at 3 decimal places. I probably could have rounded that to a 4, but hey, such is life. So 0.573 is the same thing as the sine of 35. It's an actual number. It's that ratio. So 7 times 0.573 equals x. Can I solve for x now? Will I get a number? I can, because 7 times a decimal gives me one single number, and that number is 4.011, because I do 7 times 0.573, and that equals 4.011. That is my side length x. Now, how can I check to make sure that this works? Well, didn't I say the sine of theta should equal opposite divided by hypotenuse? Shouldn't it equal this ratio? So the sine of 35, if we look back at our calculator, the sine of 35 degrees equals 0.573. But we also know that the sine of 35 should be the same thing as this ratio, x divided by 7. What is x? X is 4.011. 4.011. Divide that by the hypotenuse, so opposite over hypotenuse, divided by 7, and I should get something, again, I rounded a bit, so I should get a number relatively close to 0.573. And actually get exactly 0.573. 4.011 divided by 7 equals 0.573. That is essentially what we are landing the foundation of what we're doing right now is landing on these ratios, these trig ratios, because they are helping us solve these missing pieces, right? There's some number x that when I plug it in and do x divided by 7, it gives me the same thing as the sine of 35, that ratio. And how do we know that it's opposite over hypotenuse? Well, that's the definition of these trig functions. And so we're using those trig functions in order to solve for missing pieces, right? Use what you know to find what you don't know. That's what we're doing here. That is the main argument we're doing here. Use what you know to find what you don't know. Let's do another example. So we've got a new piece right here. Same looking triangle, different angles. These are all hypothetical, right? This is a 35-degree angle, that's 20 degrees. I just want you to think about, these are just, again, hypothetical. It doesn't have to be drawn specifically to scale. So in this case, we've got a 20-degree angle, we've got a side length of 6, and we've got a side length of unknown x. This is our right angle, and x is across from our right angle. So that means x is my hypotenuse. We've got a 20-degree angle, and we've got the adjacent side is 6, right? Because this side length BC over here, that is the opposite side of 20 degrees. So that means that 6 must be the adjacent side. So I know my adjacent side, and I don't know my hypotenuse. Adjacent hypotenuse. Which of my trig functions utilizes the adjacent side and the hypotenuse? That's right, cosine. So cosine is our function that we are using in trig land to help us solve for x. So set it up the same way we did here. Cosine of 20 equals adjacent divided by hypotenuse. Well, what's my adjacent side length? It's 6. What's my hypotenuse? X. I don't know what it is. And then what's my angle? 20 degrees. Now again, how do I identify, or how do I isolate the x? Well, when I look at my right side, it's a little bit different. Here it's x over 7, here it's 6 over x. The x is now in the denominator. So it adds an extra layer to our solving, but as you did last week on that worksheet, you practiced. There's just one extra step, it's okay. But we need to eliminate a fraction. Fractions are not our friends here. So how do I get rid of a fraction? Well, I multiply by the denominator. So if my denominator is x, I'm going to multiply both sides by x. So I do x times cosine of 20, the left side of the equation, and I'm going to do 6 over x. So x times 6 over x. The x's cancel out, and we are left with x times the cosine of 20 degrees equals 6. So it's almost like I need you to ignore that part right there for now. So x times the cosine of 20 equals 6. How do I isolate x now? Am I in a position where I can perform an operation and get x by itself? And the answer is yes. Now, if I'm multiplying some number, remember cosine of 20 is some number. If I'm multiplying that by x, how do I get x by itself? If multiplication is occurring, I need to do the opposite operation and divide. So both sides are going to be divided by cosine of 20. It cancels it out on the left side of the equation, and we're left with x by itself. So x is equal to, well, did this reduce to anything yet? I don't know. I don't know what it ends up being. It's 6 divided by cosine of 20 though, and we know that cosine of 20 is some number. So x equals 6 divided by cosine of 20, right? X has been isolated because I canceled out these, and I'm left with 6 over cosine of 20. Well, let's figure out what the cosine of 20 is. Cosine of 20 equals 0.93969262208. Round that to 0.94. So cosine of 20 is the same thing as 0.94. And so just keep it all in place the same way. X equals 6 divided by cosine of 20, which we said is 0.94. So 6 divided by 0.94 equals 6.3829787723. Round that off to 6.38. Okay, so I found my hypotenuse, my missing side length. That's 6.38. But to check to make sure that I did that right, let's plug 6.38 back into x. Let's see if I can insert an arrow here. Let's plug it in. Let's plug it back into the original. Cosine of 20 degrees equals 6 divided by x. Let's plug that in. So cosine of 20, remember we said is 0.94, is 6 divided by 6.38. Is that going to give me 0.94? And it sure does. And that is awesome news. That means that we did it correctly because the cosine of 20 should equal this decimal, 0.94. So that means we did it right. Pause this, rewind it, ask questions on the office hours document if you are wondering about any processes that we're doing here, because we're going to do a couple more here in a second, only where we're trying to find the missing angle rather than the missing side length. So again, make sure we are getting this. Go ahead and move on when we've got it. All right. Part 5. Change it up a bit. What if we know the side lengths, but we don't know the angle? What do we do now? Well, if I cover this up in a way so that I can hide the pieces of it, we've got an ABC triangle with the side length of 7, a side length of 10, and an unknown angle theta. This is the Greek letter for theta, which we often refer to as the unknown angle. It's our variable for an angle. If I want to find it, I need to use trig, right? That's all we are doing right now. We don't need to try to find, we don't use the Pythagorean, well, while we could use the Pythagorean theorem, that would only find us the third side length, not even the angle. That would not get us anywhere. We have to use our trig to find this angle. So what can I rely on? Again, like I said, the trig. But what trig? What can I do? Let's use our ratios. So with respect to our angle theta, what is 7 and what is 10? Well, the easy one, right? Angle C is my right angle, and the side length across from that is 10. So 10 is my hypotenuse. What about 7? 7, well, BC would be opposite of my angle, so that means 7 is adjacent of it, right next door to it. So 7 is adjacent, 10 is hypotenuse. This sounds familiar. Adjacent, hypotenuse, that's cosine. We need to use cosine. So the cosine of theta, notice, I don't know what theta is. I don't know what my angle is, so I'm going to plug in my 0 with the line through it, my theta. But that is equal to the ratio of adjacent divided by hypotenuse. My adjacent side is 7, and my hypotenuse side is 10. So the cosine of theta equals 7 divided by 10. Now, what do I do now? How in the world do I isolate the theta? Well, I'm going to introduce something to you guys. Just like multiplication can undo division, and division can undo multiplication, or addition undoes subtraction, and subtraction undoes division, right? They're opposite operations, squaring and square rooting. As we just learned in the last unit, taking the log and doing 10 to the power of, right? There's opposite operations for every possible function that you, or operation that we do in math. There's always an opposite counterpart to it where you can cancel each other out. And for cosine, and sine, and for tangent, it is on your calculator. I need you to look on my screen over here. The opposite, and I kind of like it because it just seems super straightforward, is going to be in these blue letters here. We've got the sine to the -1, cosine to the -1, tangent to the -1. The opposite operation of sine is sine to the -1. This is what is actually called inverse sine. So in the inverse sine of sine cancels each other out and leaves you with your angle. So let's say I'm taking, so the sine of 50 degrees is 0.766. Okay, cool. What if I want to undo this, right? What if I want to undo the sine of 50 and just get my angle by itself? Right? I'm trying to isolate the angle just like I'm trying to isolate theta here. How can I do that? Well, if I do sine inverse, so I have to hit second sine to get the blue, sine inverse of, now I'm going to hit sine again, and then of 50, right? I'm trying to eliminate the sine function, and doing the sine inverse is going to do that. I should get 50 as my answer back when I hit enter. And I do. So what this is telling us is if I'm trying to isolate some angle, I need to take the inverse, in this case, the inverse cosine of theta. Inverse cosine of cosine theta to get theta by itself. And so that's what I do to both sides, just like if you multiply one side, you have to multiply the other. So I'm taking the cosine inverse of cosine of theta. That ends up canceling out the both cosines on the left side, so I'm left with theta. And then the cosine inverse of 7/10 will give me my angle. This operation will give me my angle. This is where it starts to get kind of like you say, ta-da, you know, like it ends up giving you your answer, and it's quite convenient. So let's do that on our notes. So cosine inverse of cosine will cancel each other out and just leave me with theta. The cosine inverse of 7/10. Let's calculate that. So second, right, you have to hit second cosine of 7 divided by 10. If you just did cosine of 7/10, you're going to get a weird number. But anyways, inverse cosine, that gives me 45.57. So this is my answer. So theta equals cosine inverse of 7/10. Like I was just saying, cosine inverse of cosine cancels out. We're left with our angle. Cosine inverse of 7/10 will give me that angle, right? Angle equals this. So let's complete this operation on our calculator, and then we're all set. And we do get 45.57 like I did. So that is what this angle theta right here is equal to. All right, now let's practice with another one. So we've got A, B, C. They give us theta in a different location. Pay close attention. And we're given the side length of 4 and a side length of 16. With respect to the angle, where is 4 located and where is 16 located? Well, 16 is across from the right angle, so 16 is the hypotenuse. 4 is directly across, directly opposite of theta, so 4 is opposite. So we've got opposite and hypotenuse. Opposite hypotenuse, opposite hypotenuse, that is sine. So we're going to use the sine function to help us here. So the sine of our unknown angle, theta, is equal to opposite divided by hypotenuse. Opposite hypotenuse. So the sine of theta equals opposite divided hypotenuse, 4/16. What do we do to both sides? Give you a second to think about it. If you said take the inverse sine of both sides, or sine to the -1 to both sides to get it by itself, in this case, this is referring to the angle theta, then you are exactly right. So we're going to take the inverse sine of both sides. What does that do to our equation? Well, it cancels out the sines over here, and we're left with just our angle theta, and over here, we'll get some number. So theta equals inverse sine of 4/16. Let's compute that value. Inverse sine, the sine to the -1, of 4 divided by 16. And that equals 14.48. I'll round it to 48. 14.48 degrees. And that is our angle. How can I check to make sure I did this right? Remember, our ratios are talking about, or our trig functions always refer to some ratio, right? The sine of theta should equal 4/10. Well, 4 divided by 16, excuse me. 4 divided by 16 equals 0.25, right? A quarter. If I do the sine of this angle, sine of 14.48, I should get a number relatively close to 0.25 as my answer, and I do. That's always a good way to check to make sure you're doing your work correctly. We can check our work over for the first one as well. All right, the cosine of 45.57 should equal 7/10, or 0.7. So the cosine of 45.57 should equal 0.7, and that's exactly right. Like I said before, please pause this, go back and check your work. Make sure that this is all making sense. And this is a lot, right? This is a lot to learn and to take in, but we're going to take it one step at a time. So first, I'm going to have you guys practice with the solving for the side lengths, and then I'll have you guys practice for finding the angles. You guys rock. You're doing an amazing job, and we will go from here. So thank you guys for watching this. If you know your friends are not watching this in this class, they need to. That's the reality of this. Spring break is right around the corner, but you don't learn this now, and it's going to completely drift away. And after spring break, it's going to be like we're starting from scratch, and that'll be extremely difficult. So you got to watch it. You got to do the hard work, but you'll be rewarded with a break soon enough. So anyways, take care, guys. Let me know. Please, please, please write questions when you have them of understanding. Don't just accept this. Question things, right? Ask, how did I get this? How did I get that? On the Google Doc, please. Not via email. On the Google Doc. But yeah, thank you guys.